Have you ever looked into a swimming pool and thought it was much shallower than it really is? That's not just your eyes playing tricks. It's a fascinating effect of refraction. When light travels from a denser medium like water to a rarer medium like air, it bends away from the normal. This bending shifts the apparent position of underwater objects. We call the actual vertical distance from the surface to the object the real depth, and the depth where it appears to be the apparent depth. The gap between the two is known as the shift. In the diagram, you can see how light from the real point at the bottom travels to your eyes, making your brain perceive the image at a higher position. Let's imagine point O at the bottom of a water tank, with the surface marked as PQ. A ray traveling along OA strikes the surface normally and passes straight through without bending. But another ray, OB, hits the surface at an angle, bends away from the normal, and reaches your eyes along BC. When these rays enter your eyes, your brain assumes they have traveled in straight lines. As a result, both rays seem to come from a point I, which lies above the actual point O. This is why objects appear shallower. As you can see in the diagram, the virtual image forms closer to the surface, creating the illusion. Now let's derive the relation between real depth and apparent depth. If we look at the triangles formed in the diagram, we can apply the definition of refractive index. Refractive index, mu, is given as sine of I divided by sine of r. In other words, mu equals sine I over sine r. From the geometry of the ray paths, we can simplify this to a very useful result: nu equals real depth divided by apparent depth. Rearranging this relation, we get apparent depth equals real depth divided by nu. Let's apply this with a quick example. If the real depth is 1.2 meters and nu is 1.33, then the apparent depth works out to about 0.9 meters. The difference between real and apparent depth is called the shift. Shift equals real depth minus apparent depth, or real depth multiplied by open bracket 1 minus 1 over nu close bracket. This shift becomes larger if the refractive index of the medium is higher or if the medium's thickness increases. Interestingly, the shift also depends on the color of light. Red light bends less than violet light, so the shift for red is smaller. This is why underwater objects may appear at slightly different positions when viewed through colored light. In the comparison table, you can see that glass produces more shift than water because of its higher mu value. This phenomenon has many practical examples. A coin at the bottom of a glass of water appears raised. Fishermen know they must aim their spear below the apparent position of a fish to hit it accurately. A thick glass slab looks thinner when viewed directly from above. Swimming pools can look deceptively shallow, which can lead to risky jumps. These examples show how understanding real and apparent depth is not just about physics on paper, it's about making sense of everyday observations. Have you ever placed a stick partly in water and seen it look bent at the surface? That's another result of refraction. The part of the stick under water sends out rays that bend away from the normal as they pass into air. Your eyes trace these rays back in straight lines, placing the image higher than it really is. The submerged portion appears shorter and at an angle to the air portion. That clearly shows this apparent bending, which happens with any object viewed obliquely underwater. Let's solve an example. A coin is placed at the bottom of a tank filled with water of refractive index 4/3. If the real depth is 1.2 meters, we are asked to find the apparent depth and the shift. We use the formula apparent depth equals real depth divided by nu. Substituting the values, apparent depth equals 1.2 divided by open bracket 4/3 close bracket. That works out to 0.9 meters. Now, the shift is simply the difference between real depth and apparent depth. So, shift equals 1.2 minus 0.9, which gives 0.3 meters. This means the coin appears raised by about 30 centimeters. Let's quickly revise. Real depth is the true position of an object, and apparent depth is where it seems to be because of refraction. They are related by mu equals real depth divided by apparent depth. The shift depends on the refractive index, the thickness of the medium, and the wavelength of light. This principle explains many things, from why swimming pools seem shallow, to why spear fishermen adjust their aim, to why underwater photography needs careful angle planning. I hope you now have a clear picture of how refraction creates this optical illusion and how it plays a role in both nature and human activities. See you in the next session with another fascinating concept of physics.